Hi all, today we can discuss about ESR or EPR spectroscopy, and in almost all competitive exam at least one questions coming from this section, and it is very easy to solve, and mostly number of signals or its intensity ratio are mainly asked, and we can discuss these in 2 or 3 parts, complete ESR in 2 or 3 parts. Let's begin our video. ESR or EPR spectroscopy. What the meaning of ESR or EPR? And both are same. In some textbook ESR it is written. In some textbook it is EPR. Both are same. Okay. And ESR means electron spin resonance, and EPR means electron paramagnetic resonance. From this expansion itself, we are able to understand what is meant by ESR spectroscopy. ESR spectroscopy deals with the electron spin, and this resonance, you're familiar with this word resonance because we already completed NMR. In NMR, it is what nuclear magnetic resonance. In that section, we discussed about the resonance. Okay, so in NMR, we discussed about nuclear spin. In ESR, we are discussing about electron spin, and this full form of EPR is electron paramagnetic resonance. From this we are getting an idea about the compound which is ESR or EPR active. That is, the compound should be paramagnetic in nature, or it should contain an unpaired electron. When we are comparing with the NMR, because why comparing with NMR means, when we are discussing, you can see that almost all things we are what we discussed in NMR, that is we are discussing in ESR also, and there we are there we are considering nuclear spin. Here we are considering electron spin. That is the only difference. Other thing like splitting, number of signals, all those things are almost similar to NMR. And in NMR we are considering nucleus, and in ESR we are considering electron. And for a compound to be NMR active, there should be a nuclear spin, or nuclear spin should not be equal to 0. That we already discussed. C12 is NMR inactive, but C13 is NMR active. And there also for proton, C13, F19, P31 all have I value 1/2. That means for a compound should be NMR active, that there should be some nuclear spin, or the I value should be greater than 1. And similarly, we can tell if for a compound to be ESR active, the electron spin should not be 0, or there should be an electron spin. That means S value not equal to 0. For a compound, if a compound have an unpaired electron, then the spin will be 1/2. That means S value is not a 0. If a compound contain diameter or unpaired electron, then overall spin will be 0. That time it is not ESR active. Okay. We can consider one example. First, we can consider C2 molecule, and that means two carbons are combined, and each carbon contains 6 electrons, and overall 12 electrons are there. In C2 molecule, overall 12 electrons are there. We can arrange, or we can distribute the electrons in orbitals. Then sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2. Pi 2px equal to pi 2py, because these two are in same energy level. If you are writing that diagram, then pi 2px and pi 2py in like degenerate. So first we have to fill, like it's based on Hund's rule. First we have to distribute electron as first we have to give electrons to both, then only it will pair. Then sigma 2 px2 pi 2 px2, pi 2 py 2, 4, 6, 8, 10, 12. Then we completed, or we filled the electrons in this MOs. And now considering this, because here almost everything is filled, or here you can see that this orbital also completely filled. That means the compound is diamagnetic in nature. In that case, overall spin will be 0. Then the compound is said to be ESR inactive. Clear? And this distribution you have studied in your lower classes. If you don't know how to how these are coming, or how we can write this MOs, those things. If you don't know, you please mention. I will do one video based on this. And if number of electron is less than 14, then there should be some mixing, otherwise it won't mix. For oxygen molecule, there is overall 16 electron. That also we can feel. Sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, and sigma 2p set. Here you can see that in the case of C2, pi orbital come first, or pi orbital have lower energy than sigma orbital. In the case of O2, sigma orbital have, sigma 2p set have lower energy than pi orbitals. Sigma 2p set, pi 2px2, pi 2px 2py2, pi star 2px1, pi star 2py1. 2, 4, 6, 8, 10, 12, 14, 15, 16. Here you can see that this also based on Hund's rule. Here you can see that in each orbital one unpaired electron is there. That means the compound is paramagnetic in nature and it is ESR active. When we are considering that VSEPR theory or VBT theory, in all cases, but we cannot explain how that paramagnetic nature of oxygen coming. When it transferred to MO theory, this problem solved. Here you can see that this oxygen molecule is paramagnetic in nature. That means ESR active. So a compound should be ESR active if the electron spin is not zero, or if electron have a spin, or if the compound contain an unpaired electron, or if it is a paramagnetic, that means it is ESR active. If the compound contain a paired electron, then it is ESR inactive. That is the idea you have to build. That ESR means electron spin resonance, or it can be another name of ESR is EPR. It is electron paramagnetic resonance. For a compound to be ESR active, there should be unpaired electron. That is the only condition. That means electron spin should not be zero, or there should be an electron spin. Clear? Now we can consider the degenerate levels of electrons. This thing we discussed in NMR, that how that levels are coming, how the splitting is coming. Similar to that, here also we are explaining, but in this case it is based on electron. There it is based on nucleus. So number of degenerate level is equal to 2s plus 1. For a single electron, if you are considering a single electron that have a spin of 1 by 2, so number of degenerate level will be 2s plus 1, that is equal to 2. Then there should be 2 degenerate levels like this. Degenerate levels mean these have equal energy or equal population. That is mean by degenerate level. And this degenerate level have level means plus 1 by 2 and minus 1 by 2. Now these two have same energy. It is in the absence of magnetic field. When we are applying magnetic field and this degeneracy breaks, and the levels will split into 2. Here in absence of magnetic field, the levels are degenerate. When we are applying magnetic field, then it split into 2. And the energy we can write as ms mu g b0, where ms means it represents the electron spin, and mu represent Bohr magneton. In some textbook it is beta also, it is represented by beta, and don't confuse with the mu or beta, it is Bohr magneton. And another factor is G, that is known as Landé factor. Landé factor have a we can find out Landé factor, and that value is 3 by 2 plus S into S plus 1 minus L into L plus 1 divided by 2 into 2J into J plus 1. And for electron, the G value is approximately equal to 2. It's not equal to 2, it has some plus or. Here the value ms, first we can substitute the value minus 1 by 2, then the energy will be lower in energy, because minus value means negative energy, or lower energy means lower level, minus 1 by 2 mu g b0. When we are substituting the value plus 1 by 2, then it represents the upper level energy. So we have two energy level. In the absence of magnetic field, it is a degenerate level. When we are applying magnetic field, the degenerate state split into two energy levels, one lower energy with the value minus 1 by 2 mu g b0, and higher energy level plus 1 by 2 mu g b0. Okay, now we can find out the energy difference between these two levels, upper level minus lower level, and then we are getting a value of mu g b0, right? Then the energy difference here, delta E, is mu g b0, and from that we get a value for frequency mu g b0 by h, because energy have a value, delta E have a value h nu, and while substituting that value we are getting frequency mu g b0 by h, and this mu g is a constant for a particular electron or species. Then we can write as gamma, and that gamma is known as gyromagnetic ratio. For a particular atom, it is a constant. Okay, then gamma h means gyromagnetic ratio for hydrogen. It is 42.57 megahertz per Tesla, and this gyromagnetic ratio for electron is 28,000 megahertz per Tesla. That means you can see the difference between this gyromagnetic ratio, and this gyromagnetic ratio is directly proportional to what? Delta E, right? Delta E equal to mu g b0, or this mu g is what? Gamma, and delta is directly proportional to gamma. That means when we are considering the electron, the energy difference is very high compared to the proton, right? That means we know that this NMR range, or NMR, the energy difference is small in NMR. That is why it is in the radio wave region. And in ESR, the energy difference in ESR means when we are considering electron. In the case of ESR, the delta is very high, so it is absorbed in microwave region, or microwave radiations are used in ESR. In NMR, radio waves are used. In ESR, microwave radiations are used. That is an important point. NMR region is radio wave and ESR region is microwave, because of this difference in the gyromagnetic ratio, and which lead difference in the energy. And for NMR, the energy difference is very small. For ESR, the energy difference is very high, so that NMR is in radio wave region and ESR in the microwave region. This is an important point. Sometimes this question will ask the region of ESR or region of NMR. NMR is radio wave, ESR is microwave. That point you have to remember. And this equation for frequency, that also you have to remember, because mostly the questions asked from this section is the calculation or numerical part. Frequency and this magnetic field, for two or three values will give, and fourth one we have to find out. Frequency and B0, magnetic field versus frequency. Some questions will ask that you have to answer, or it's simply, if you know the equation, it's very easy to do. If you don't know the equation, you are not able to do that. Okay, that we can discuss in later. So this equation you have to remember: delta E equal to mu g b0 or gamma b0, and nu equal to gamma b0 by h. Fine. And this point also you have to remember. NMR is in radio wave region and ESR is in the microwave region. Now we can discuss about ESR signal. And ESR signal is a plot of intensity versus G, I versus G. G is what? Lambda factor. But it gives a broad signal, and that is due to, like this, when we are plotting intensity versus G, we are getting a broad signal. Here broad signal is obtained based on the Heisenberg uncertainty principle. According to Heisenberg uncertainty principle, delta W into delta T is a constant. That means width and relaxation time, they are inversely proportional, or width is inversely proportional to the relaxation time. For an electron, the relaxation time is very less. So as it is inversely proportional, when the relaxation time or the time is less, then width will be more means broad. That's why we are getting a broad signal, as the relaxation time of electron is very less. That time we have to take what? The derivative. Then the plot will be delta I by I versus G, and this G means it's almost similar to the delta value in NMR. NMR we are taking the chemical shift value, almost same meaning have for this G value. And ESR plot means it is intensity versus G. Then we are getting a broad signal, so we have to take the derivative, delta I by I versus G. Maybe you can maybe some question you can expect, like what is the plot of ESR. Okay, and this G value for electron is almost equal to 2. Now we can consider the interaction of electron spin with the nuclear spin, or the splitting of lines. In NMR, what we considered, or let's take a proton NMR, or let's consider proton NMR. In proton NMR, first we have to find out how many non-equivalent protons are there, and that much signal we are getting, right? How many number of non-equivalent proton, or in the case of C13, how many non-equivalent carbon 13 carbons are there, that much signal we are getting. Number of non-equivalent nuclei equal to number of signals. Okay, here after that we are splitting. How we are considering for a particular signal, we have to consider its neighbors. Its neighbors cause the splitting, right? In a 2ni plus 1 in 2ni plus 1, when there is multiple neighbors, then we have to multiply the values. Like that we consider the splitting of the line, right? Here also similar way we are considering. First we can see the diagram. Let's suppose only one electron is interacting with a nuclei of magnetic nuclear spin I equal to 1 by 2. We are considering an electron is in contact with a nucleus with a nuclear spin of value I equal to 1 by 2. This splitting we have discussed in previous slide, that in the absence of magnetic field, there is two degenerate levels, and when we are applying the magnetic field, it is split into two. One is with a ms value minus 1 by 2, other with ms value plus 1 by 2, or ms means electron spin. Now we are considering that nucleus is causing the splitting, and the splitting will be 2ni plus 1. Here we are considering I value as 1 by 2, and only one nucleus is there. 2 into 1 by 2, 2 into 1 into 1 by 2 plus 1, that is 2. So we have mi value plus or minus 1 by 2, right? I think this much okay. Now we have to consider the splitting. That means this line also, first we are getting two lines or two levels, and each level will split into two because of the nucleus. Here in the absence of magnetic field, both the levels are degenerate. When we are applying a field, it is split into two, and when we are contacting or when we are interacting with a nucleus, each level will split into two, like this. Okay, now we have to find out the energy values. Here this is ms value is minus 1 by 2, and here ms value is minus 1 by 2, that much okay. Now we have to consider mi values. Mi value here I have written plus 1 by 2. Here I have written minus 1 by 2. And some of you have the doubt. Minus value will come down, right? Minus value means negative value means lower energy. Here an easy way to understand this is just multiply these two. Minus 1 by 2 into plus 1 by 2. Minus 1 by 4. Here you multiply both. Minus 1 by 2 into minus 1 by 2 plus value. This is a minus value, this is a plus value. So negative value have the lower energy. So the value will be ms minus 1 by 2 mi plus 1 by 2. And this have a value ms minus 1 by 2 mi minus 1 by 2. Now we can consider the upper level. This upper level also split into 2. Here ms value is plus 1 by 2. Here mi value we have to take minus 1 by 2. And here ms value is plus 1 by 2, mi value is plus 1 by 2. Okay, just multiply, then negative value will come in lower level and positive value higher level. And this is what the splitting. Now we have to consider, now we have to find out the number of signals that we have obtained. For that, selection rule is there. And the selection rule for ESR is delta ms equal to plus or minus 1, delta mi equal to 0. This is the selection rule for ESR. And we already discussed about rotational, vibrational, rotational Raman, vibrational Raman, all most bare, all those things. In everything we have some selection rule, right? Those selection rules, first you have to list out the selection rule. A lot of questions you can expect from that also. Just write down all the selection rule, then only you will able to understand, because all the time it is plus or minus 1, 0, plus or minus 1, like that lot of values are there. So you have to list down all the values, all the selection rule, and study well. And here the selection rule is delta ms equal to plus or minus 1, delta mi equal to 0. Now we have to consider how many signals we are getting. First we can consider this value delta mi equal to 0, that is delta mi is equal to plus 1 by 2. So plus 1 by 2 to plus 1 by 2, only one value is there, then only it will become what? 0. If you are considering plus 1 by 2 to minus 1 by 2, then the value will be minus 1, right? So that is not coming in the selection rule. So first we have to consider mi value. That is very easy. Mi value equal to 0, then we have to consider this signal, that is mi, this lower level to higher level. Then mi equal to 1 by 2 minus 1 by 2, that is equal to 0. Now we can check whether this delta ms equal to plus or minus 1 also satisfy. Upper level is 1 by 2, lower level is minus 1 by 2. Minus 1 by 2 minus 1 by 2 equal to plus 1. Then it's both the selection rule is okay for this transition. Now let's consider the other one, mi equal to minus 1 by 2 to mi equal to minus 1 by 2. Here also minus 1 by 2 minus 1 by 2, it's 0. Plus 1 by 2 minus 1 by 2, that is equal to 1. So only 2 transitions are possible. So number of lines or number of signals equal to 2. And when there is 2 more electrons and more number of nuclei, that the kind of lines or the splitting pattern, it's very difficult to draw. So this is only for information, and you don't need to do these things for your exams. There is shortcut for that. This is only the concept. This is how that splitting happens, and how this transition happen. Number of signal, every time we are writing number of signal, and what is mean by that number of signal, that I think now it's clear for you what is mean by all those things. And in this section you have to remember this selection rule, that is very, very important. Selection rule for ESR is delta ms equal to plus or minus 1, delta mi equal to 0. Okay, let's have some examples. We have to find out the number of ESR signals. First example is H2 molecule. For H2 molecule, there is 2 hydrogens, and the total number of electrons is 2. Then we can write as 1s2. That means both are paired, or it is a diamagnetic compound. That means it is ESR inactive. Now we can consider H2 plus. H2 plus means 1H combined with H plus, and overall electron is 1 electron. 1 electron means the configuration will be 1s1. That means it is paramagnetic compound. It have 1 unpaired electron. That means it is ESR active. Okay, this point I think it's clear. For H2 that it is diamagnetic, it is ESR inactive. For H2 plus it is it have only one electron, one unpaired electron, so it is ESR active. And now we can consider number of signal. Here you can see that both the hydrogens are, it's a hydrogen, right? This proton have a spin of 1/2, so it is an active nuclei. It is able to split the line. Number of signal will be 2ni plus 1, 2 into 2 into 1/2 plus 1, that is equal to 3 signal. 3 signal you are getting. Okay, number of H1 nuclei is NMR active, it is equal to 2, and it is NMR active nuclei. Sorry, not NMR active nuclei, that's okay, but it have an electron spin, it have a nuclear spin, so it is able to split. So the number of signal will be 2 into 2 into 1/2 plus 1. Okay, once again, as it contain unpaired electron, it is ESR active, and as there is a H1 nuclei that is an active nuclei, that active nuclei have a capacity to split in 2ni plus 1 times. So the value will be 2 into 2 into 1/2 plus 1, that is 3 signal we are getting. Third compound, Hd plus. Here also one electron is there, and that it's active, right? It's active. And the number of signal will be, in the case of splitting only the difference coming. Here one is hydrogen, other is deuterium. Both have different both have different nuclear spin. H have 1 and H1 have 1 and D have 2, nuclear spin 2. The number of signal will be 2ni1 plus 1, 2ni2 plus 1. Then 2 into 1 into 1/2 plus 1, 2 into 1 into 1 plus 1, that is equal to 2 into 3. 2 into 3, 6 signal we are getting. And it's almost similar to the NMR. If you did not watch the video, please watch those videos. You can check the playlist in that spectroscopy. One folder is there, in that lot of almost all spectroscopic videos are there, and I think it is more than 15 or 16 videos are there. Okay, 15 videos are there. You can see those things. I will give one link in the description box, also in the I button. You can just check those videos. Okay, now here we are getting 6 signals. Now it's methyl radical. This question asked in GATE 2004, GATE 2019 in PSC exams. This methyl radical, lot of time questions are asked. And here also one unpaired electron is there. That means one signal is there, and how the signal splits. Here you can see that 3 hydrogens are there, and all are this hydrogen means, or this H1 is an active nuclei, so it is able to split the signal. Number of signal is 2ni plus 1, 2 into 3 into 1/2 plus 1, that is equal to 4. 4 signals you are getting. And similar to that, CD3, this also very important because in almost all exams or competitive exam, you can see how many number of ESR signals you are getting from CD3 radicals. And it's added in June 2014, also June 2018. And here also one unpaired electron is there, that means ESR active, and how it's splitting, how the splitting comes. 2ni plus 1, 2 into n is 3, D or deuterium is an active nuclei with a spin of 1, 2 into 3 into 1 plus 1, that is equal to 7. Now NH2 radical. Here you can see that nitrogen is an active nuclei. Also this H1 is also an active nuclei, that is 2 active nuclei are there. So the number of signal will be 2ni1 plus 1 into 2ni2 plus 1. Here first we can consider a nitrogen. 2 into 1 into 1 plus 1. This nitrogen have a nuclear spin of 1, and this proton have an, or that H1 have a I of 1/2. 2 into 2 into 1/2 plus 1. Here we are getting 3. From this also 3. Overall 9 lines are there. About the intensity, we can do video in next class, because that for I value, if I value is less than or equal to 1 by 2, we are adopting Pascal triangle, and if it is the I value is greater than 1 by 2, we are adopting non-Pascal triangle. And Pascal triangle, it is easy to find out the intensity ratio, but for non-Pascal triangle, it is quite different way, or it's quite difficult. So that that intensity related thing we can do in another video, and how we are able to solve the non-Pascal triangle, that one video I will make. Then you can do any questions from this section. Okay, now just we have to find out the number of signal, that much only. Next, CD3, CD2. Here one radical is there, and here two types of deuterium is there. That means number of signal will be here again 2ni plus 1 into 2ni 2 plus 1. First we can consider this 3, this CD3, 2 into 3 into 1 into 1 plus 1, and this D2 2 into 2 into 1 plus 1, that is from here 7, from here 5, overall 35. In NMR we have discussed all these things, okay, the calculation. That's why I think no need to explain more. Just if you're getting an idea, it's okay. That's why NMR and ESR are almost similar. But in NMR we are considering nuclear spin, but in ESR we are considering electron spin. Now consider this compound. Here one radical is there, or one unpaired electron is there, that means ESR active. Now we have to consider splitting. For that we have to find out any active nuclei is there. Here hydrogen is there, that is able to split the line. So how many types of hydrogens are there? First we have to find out those things. So this is first type of hydrogen, second, third, fourth. So overall 4 types of hydrogens are there. All are different, so all split separately. And the number of lines will be, first this one, 2 into 2 into 1 by 2 plus 1. Now consider this second one, 2 into 2 into 1 by 2 plus 1. Third type of hydrogen, 2 into 2 into 1 by 2 plus 1. And this fourth one, 2 into 1 into 1 by 2 plus 1. Overall 54 lines are there. Next question. This is anthracene molecule with a radical. So it have an unpaired electron. Now we have to find out types of hydrogens. 1, 2, 3. 3 types of protons are there. So number of lines will be like this. 2 into 2 into. Now first we can consider this first proton. 2 into 2 into 1 by 2 plus 1. Now this second proton is 4. 2 into 4 into 1 by 2 plus 1. And this third proton also 4. 2 into 4 into 1 by 2 plus 1. 3 into 5 into 5. Overall 75 lines are there. Now we can consider this germanium, some alkyl compound, germanium alkyl 3 with a radical. So radical is there, that is unpaired electrons, unpaired electron is there. So here it's given that I value of germanium, just substitute the value, that much only. Number of line 2ni plus 1, 2 into 1 into, only one germanium is there, so 1, 9 by 2 plus 1, that is spin is 9 by 2, then overall number of lines will be 10. This question asked in NET June 2017. I think now you got some idea regarding this ESR1. Next, in coming video we can discuss about the Pascal and non-Pascal triangle. Also for transition complexes, it's a little different from this normal one. This is almost main group elements, but when we are coming to transition metals, some points we have to remember. Then about G parallel and G perpendicular, and 2-3 videos this ESR will finish. In most of the case, the question is from number of signals. How many number of ESR signal you are getting? Questions asked from those areas. So I think now you got some idea regarding this thing. If you have any doubt, you can comment, and if I did some mistake, that also you can comment. Okay, that much. If you like this video, like, share and subscribe chemakhilam. You can follow me on chemakhilam Insta page, Facebook, So you can direct mail me at chemakhilam@gmail.com, and please press the bell button. Then you will get videos when I am uploading. Thank you for watching.